Hi, I'm UC Lee. In this video, we introduce projective parallel single-pixel imaging, which is a photography method to overcome global illumination in 3D reconstruction. For obtaining 3D data, frame projection profilmetry, which is referred to as FPP, is a typical structure light method. However, industrial parts often embodied with complex structure and materials. This leads to global illumination, which causes failure cases. In this video, we focus on solving 3D reconstruction under interreflections and subsurface scattering. Interreflections occur in groove structure composed by metal. The captured patterns are overlapped patterns mixed by direct and interreflections, which cause data missing. Single-pixel imaging method can be used to separate direct light and interreflection. In the upper left figure, the light transport procedure is shown. For camera pixel, the captured light, which is colored by yellow, is a mixture component composed by direct light, which is colored by green, and interreflections, which is colored by blue. Thus, the observed grayscale of a pixel is mixed, and separating them is challenging. However, from the perspective of projector, the source of direct light and interreflections are different. The result of single-pixel imaging method is exactly the image from the perspective of the projector. By using single-pixel imaging, the light transport coefficients are captured, and the direct light and interreflections are naturally separated. Subsurface scattering occurs in translucent surfaces, where the direct pattern is degraded by the transmitted scattered light. This can cause large phase error. Situation is similar for subsurface scattering by using single-pixel imaging. Direct light and subsurface scattering are naturally separated in light transport coefficients. In our previous method, we introduced parallel single-pixel imaging for capture light transport coefficients efficiently. However, capturing the 2D light transport image can be time-consuming. In this paper, we further accelerate the capturing efficiency by reducing the 2D light transport image to multiple 1D projection functions. We call this method projective parallel single-pixel imaging, which will be referred to as PPSI. Here is an overall framework of the proposed method. First of all, we have to answer a consistency question, that whether the correspondence point found by PPSI is the same with the correspondence found by parallel single-pixel imaging. This consistency analysis builds the basics of the proposed method. Given this basics, direct illumination correspondence matching and efficient projection functions capture are studied. To answer the consistency question, we introduce local maximum constraint. This constraint tells us that the direct illumination point in the light transport coefficient is preserved as a local maximum in the projection functions. Thus, each projection function provides a constraint for the position of the direct illumination point. If this projection function can be obtained, the direct illumination points can be calculated by first vertically reversing the local maximum and then making intersection, just as shown in the right figure. To capture projection functions efficiently, we came up with local slice extension method, which involves a coarse to fine procedure. We show the generation equation for coarse location patterns. The coarse projection function is calculated by inverse Fourier transform. We also provide the equation for how to arrange the captured intensities to obtain the Fourier coefficients for inverse Fourier transform. Here, we provide the generation equation for fine location patterns. By applying inverse Fourier transform, the fine location projection function patches are obtained. Lastly, we merge the coarse and fine information by first periodically extending the fine projection function patches and then preserving the regions where the coarse projection functions are non-zeros. A comparison between FPP and PPSI is shown. Strong interreflections dominated. PPSI is able to reconstruct complete 3D data. Subsurface scattering is dominating in these senses. PPSI is still able to reconstruct complete data. We also compare macro phase shifting method with PPSI. Macro phase shifting method cannot reconstruct complete 3D data for the interreflection senses. For the translucent senses, there are always ripple errors on the data. Thank you very much.